Now we're going to talk about percentiles of a distribution, and that is a word that you might be familiar with. You might have seen that word, let's say, on your report card for a standardized test, like you took the SAT or the ACT, and they said that your score put you in the 80th percentile. Well, what does that mean? Well, let's go ahead and give you a definition of a percentile and then show you how it relates to one of these random variables and the distribution. So if a score, and that would be like one of our x values, is in the 80th percentile, then this score, the score x exceeds 80% of all scores, right? So it exceeds 80% of all scores. And it is less than 20% of all scores. All right, so let's kind of visualize what this means. So what I'm going to sketch now is the PDF of one of these continuous random variables. So let's say, the PDF looks something like this. And I'm going to mark my score, let's say, here. If this is in the 80th percentile, right, then what that means is 80% of the area under the PDF is to the left of the score, right? So you'd have 80% of the distribution, right, would be down here. So this would be 80%, or we could say just 0.8. And then the remaining 20% would be over here, because remember, under the PDF there has to be a total area of 1, right? So you got 20% there, or your 0.2, right? And this means that this score is in the 80th percentile. So it is larger than 80% of all the values in this distribution. So like, think of your sample space now, this entire interval, right? This specific x value will represent the 80th percentile if 80% of all the scores are less than it, and then 20% are greater than. So what that means in the context of probability now, the probability that my random variable is less than or equal to this x, right? Again, if my x represents the 80th percentile, well, that will be 0.8, because again, this probability corresponds to the area that's to the left of this value. Now, we can refer to it as x, but it would be nice if the symbol that we use to represent this specific number also indicates what the percentile is. And there are lots of different notations for the percentile, but I like this one that I'm about to introduce, because it's simple, and it conveys exactly what we need it to mean. And what we do is we put the 0.8 as a subscript to indicate that this is the 80th percentile, right? So really there should be we'll put a 0.8 there, right? So this notation indicates the 80th percentile of the distribution, and that is the specific number in our sample space, where in this case 80% of the distribution is to the left, and then the remaining 20% is to the right, right? So let's actually formally now define what a percentile is, right? So this is our formal definition. So let P be a number between 0 and 1, right? So it looks like a probability. And I mean, based on this, you can see that it is related to probability. So let P be a number between 0 and 1. The 100 times pth, I'll write it like this, percentile of the distribution of a continuous random variable x, and let's write down the notation for it. So just making it more general now, so it's going to be a little x, and we're going to put the p right there, right? So in this case, our p was 0.8, right? And that is our number between 0 and 1. So this is our notation, and this is how it's defined. So it is defined by right? So it's the probability. So in fact, let me write it like this. So if we were to, and I'll express this in integral form first. So if we integrate from negative infinity up to our pth percentile, p there, and what would we integrate? Well, we would integrate the PDF, right? That would give us exactly p, right? So it would give us the number p. Again, going back to our little sketch there, in this case, that p is 0.8. But this is exactly how we define our CDF, right? It's in fact, I'm using the notation of here. This is the exact notation of our CDF. So we could also say that this is equal to our CDF evaluated at the percentile, right? So these two equations here give us two ways to find our x sub p. So if I know what percentile I'm looking for, I would either use calculus on this side, and I have to do an integral and kind of have this placeholder for my upper limit, and then I would set that equal to p and solve for x sub p. Or if I happen to have my CDF, then I just set my CDF equal to that number and again solve for x sub p, right? So depending on what's given, we can use either of these equations to figure out what the percentile is. All right? So let's do an example of this to kind of illustrate this concept. Right? So let's look at, and I'll choose a fairly simple PDF. So let x be a continuous random variable with, let's say we have our PDF, and this is how it's given. And I'm going to choose a linear PDF. So this will be 1/3 x plus 1/6. And then the sample space for this one is the interval x between 0 and 2. And it actually doesn't matter if I include the endpoints or not. So, and then 0 otherwise. All right, so there's our PDF. Now let's go ahead and find the CDF, right? So that will be a good little exercise. So now remember, the CDF, we have to do it in like pieces. So for instance, when x is less than 0, right, the CDF will be the 0 function. So when x is less than 0, right, because again, the smallest possible value of x in our sample space here is 0. So if our x is less than 0, then our CDF is going to be 0. When x is between 0 and 2, that's where we have to go through and compute the area function of this. So we have to accumulate the area, right, under the PDF. So when x is between 0 and 2, we have to set up our area function. Now the area, the region starts at x equals 0, and then it's going to go up to x, right? And then we're going to integrate 1/3 t plus 1/6 with respect to t. So that's where we replace the variable x in our PDF with this dummy variable or placeholder in order to have a well-defined area function, right? But the linear function is simple enough that we can go ahead and evaluate it, right? We can go ahead and evaluate our integral. So we have 1/6 t squared plus 1/6 t evaluated at 0 and at x. So when we evaluate it at the upper limit, we have 1/6 x squared plus 1/6 x, and then at the lower limit, everything is 0. So this is our area function that accumulates the area when x is any number between 0 and 2. Now once your x is greater than or equal to 2, then it would have accumulated all the possible area, and then we end up with 1. So to kind of complete this, we say when x is greater than or equal to 2, our CDF is a constant function, but then it would have a constant value of 1, right? So let's write the CDF down in piecewise form. Right? So it's 0 when our x is less than 0, and then it's this quadratic x squared plus 1/6x whenever x is between 0. So again, if you want to, if it helps, you can certainly put the equal signs here, right? And then you could say that it's 1 whenever x is greater than 2. All right. So now we have our CDF. Let's go through the process of computing some percentiles, right? So let's start with something like the 20th percentile. So x sub 0 point, or the 25th percentile. So to find the 25th percentile, we solve this equation. So in other words, we want to know what number, when I plug it into my CDF, will give me a value of 0.25. So 0.25, right? Well, it certainly can't be a value of x less than 0, right? Because anything less, when any x value less than 0, that gives me a CDF value of 0. And it can't be anything greater than 2, because if I plug anything greater than 2 into my CDF, it's going to give me a value of 1. So the solution would have to be somewhere between 0 and 2. That makes sense, right? Now, it might be a little confusing having the x sub 0.25 here and then a 0.25 here. If you wanted to use some other letter that's not that, necessarily confusing, something a little bit easier, maybe you just want to use a letter like A, something that isn't already being used in the problem, you can, right? So for instance, if you wanted to make your work a little bit easier, and say, okay, let's find the number A that when I plug it into my CDF, which would be this part of the CDF, that I get a value of 0.25, right? Well, let's set it up. So this would be 1/6 A squared plus 1/6 A. And I'll go ahead and write this as a fraction, so 1/4, right? And if we multiply through by 6 and 4, so if we multiply through by the lowest common denominator, just to clear the fractions, I will get 4A squared plus 4A is equal to 6. And then what I'm going to do is write this quadratic equation in standard form. So I have, let's see, so 4A, well, in fact, actually the lowest common denominator is 12. So what I can do is I can simplify the equation once. Let me write it in standard form, and then let's go ahead and divide through by 2. That'll make it a little bit easier. So we have 2A squared plus 2A minus 3 equals 0, right? Well, I'm looking to see if this is factorable, and it's not, right? It's not factorable because I can't find factors of -6 that add to give me a +2, right? So I'm going to go ahead and use my quadratic formula. So that is negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So 2 times 2, right? So under the square root, well, actually, let's see what's going to happen here. We have -2 plus or minus. Under the square root, I have, so this is 8. So I have 28 there. So I have root 28. And then this is all over 4. I can take out a root 4. So let's reduce this a little bit more. So -2 plus or minus root 28 is 2 root 7, and then over 4, and then now I have a common factor of 2, so I can reduce it to -1 plus or minus root 7 over 2. So as expected, it shouldn't be surprising that we end up getting a two solution. So either A is -1 plus root 7 over 2, or A is equal to -1 minus root 7 over 2. But again, based on what was said, this number is negative, right? But the sample space for this distribution consists of numbers between 0 and 2. So it would have to be this value, right? So I'll just indicate that this is not in the sample space of X, right? But we do get an irrational number. The decimal for this, however, if we round it to 4 decimal places, so A is approximately 0.8229, right? And we see we get a number between 0 and 2. So what this means, now as I said, I started with that linear function, that linear PDF, something like this, and it goes from 0 to 2. So what this is telling me now, this number in my sample space, which is just shy of halfway between 0 and 2, the roughly 0.8229, it has, remember this is our 25th percentile, so it has 25% of the area to its left, right? And then so that blue area there is 0.25, and then we would then know that the remaining 75% of the area would be to the right. But again, it would stop at the largest possible value of x. So this is the 25th percentile of this distribution, right? So it's not quite really in the middle, and you can see because our distribution is this linear function that with a positive slope, it makes sense that you have fewer, not fewer, but less area to the left here, and then a lot more to the right, right? So this is our 25th percentile. Now, there's another important percentile, the one where it kind of breaks the distribution exactly in half, the 50th percentile, also called the median. All right, so to find x sub 0.5, right, also known as the median, right? Again, you might tend to think, yep, it should be, 1. It should work out to be 1 because 1 is halfway between 0 and 2. But that's not what you're splitting up. You're not splitting the sample space in 2. You're splitting the area in 2. So in other words, we want exactly half of the area here to be to the left and then half of the area to be to the right. Well, how do we do this? Well, it's the same thing. We'll have to do the exact same process, but the only difference is we're going to put 1/2 right here because we want exactly a half of the area to be below and a half to be above. So that means we would want our CDF to be equal to 0.5, right? So I'll use the same letter A, right? So we solve this equation, 1/2, right? So remember, we have our 1/6 a squared, and then we have our plus 1/6 a, and now we have 2 over there. Let's multiply everything by 6. Again, just clearing the fractions. So we have a squared plus a is equal to 3, and then move the 3 over, right? So we got a squared plus a minus 3 is equal to 0. Again, we can't find factors of -3 that add to give us a positive 1. Right? So once again, we're going to have to use our quadratic formula. So in this case, a is -1 plus or minus the square root of 1 squared minus 4 times a times c all over 2a. Now, when I say a, we're talking about the leading coefficient here. So we end up with 2. So what do we have under the square root? Oh, another irrational number, right? And that's always going to happen when our thing isn't factorable. So we end up having 1 plus positive 12, so that's 13. And then in the denominator we have our 2. So there's no breaking this down. We already have a prime number under the square root. So that's pretty much it. So here are our 2 solutions to this quadratic. So either a is -1 minus root 13 over 2, or a is -1 plus root 13 over 2. But this one, again, is negative. The numerator is definitely negative, so the entire fraction is negative, which means it's not in our sample space, right? So even though we get a solution, it's not a valid one, right? So not in the sample space of x. So this would have to be our 50th percentile or our median, and then it better be a number between 0 and 2, otherwise we would have messed up in our algebra. But this is a value between 0 and 2, it ends up being 1.3028 roughly, right? So again, if we sketch this, here's our sample space. Again, 0 to 2. And our PDF was that linear function, so it looks like this. So the median is actually a little bit past the midway point of our sample space, right? So there would be 1. So the median is somewhere over here. So this is our x sub 0.5, which is equal, or approximately equal to what we just found, the 1.3028. And visually, what it means is, right at that line, we now have a 50-50 split in the distribution. So we have 0.5 of the area there, and then the remaining 0.5 of the area there, right? So that's how we can find, so finding the percentiles, once you have a relatively simple CDF, or you can find the CDF relatively easily, it's a matter of algebra. Now, since you're going to be setting these functions equal to numbers like a half or 0.75 or 0.9, depending on what percentile you have to compute, you know, you'd want to be able to solve it quite easily. But if, for instance, you end up with an equation that isn't solvable using just, basic algebraic techniques, that's why sometimes you end up having to approximate it using some root finder, or maybe some software like MATLAB or Excel has a solver built in. But finding percentiles using a CDF ends up being just an algebraic process, right? So hopefully you found that interesting, and now you not only know what a percentile is, but you can find it once you have the distribution or cumulative distribution function. All right, see you in the next video.